A lifetime of hard work, children laughing in the kitchen, family photos on a restaurant wall, a legacy that lives on. It all comes from the power of a conversation, like the one Tommy Hall had with First Horizon Bank about taking over his father's Charleston-based restaurant business. Now the table is set for a whole new generation. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. First Horizon Bank, member FDIC. Recently, our client John met his banker to discuss plans for a clean energy building. What he found was a shared passion for building something more. Momentum for change. First Horizon Bank. Let's find a way. Go to firsthorizon.com/John.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello once again. Thank you for joining us. This is the Space Nuts podcast. My name's Andrew Dunkley, and with me, of course, momentarily, is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. I just realised that, yes, my power had dropped out again. It fell out when I plugged in the mic.
I'm doing the introduction and all of a sudden you're not there, and I'm thinking, uh-oh.
Yeah. Oh, where's he gone?
We're off to a great start. We're off to a fabulous start. Oh, dear.
Well, all right. Let's just keep going, eh?
That's the way you do it. That's the
way you do it.
That's one of the rules of radio. If something goes wrong, just keep on going.
Keep on going.
It works rather well.
Ooh, I'm going to do something else.
Oh, okay. Nice shirt, by the way.
Okay.
It's a lovely shirt.
Oh, I'm glad you like the shirt. Yes, I got it one day when I forgot to go to take my stuff to Port Douglas. There we are.
Terrific.
We're all set now.
We're all good.
Sorry.
You can see how professional we are. We're always so prepared. Today, Fred, we're really interesting stories. I'm quite tickled by this first one, which is basically the passing of a new law to protect sites. Now, we do that on Earth, but this is to protect sites of significance in space history, I suppose, such as the footsteps on the moon made by Neil Armstrong, presumably the very first one, if it's still there. And I'm guessing other places of significance. We're also going to look at, this is an intriguing story as well, the detection of gravitational waves using an observatory the size of a galaxy. How long did it take them to build that, I wonder? And we're going to get some questions from Jonah in Houston and Jacob in Phoenix. And I will say, actually, we're a bit light on for questions at the moment. Maybe that little binge we did before Christmas, Fred cleaned it all out, and everybody's on holidays and letting their brains relax. And we're just a bit short, but that's okay. We'll tell you how to send your questions in a little later. But first, Fred, this law that I believe has actually been passed and ratified to protect places of significance beyond Earth, that sounds like a fabulous idea.
Exactly, yeah, and it is. It's something that's been sort of brewing for some time. We have here in Australia, we've got a very prominent space archaeologist by the name of Alice Gorman, who's one of the things that she pushes for is exactly this kind of legislation. I haven't spoken to Alice recently, so I don't know what she thinks of this, but this is legislation that has been passed in the United States. It passed on the 31st of December. It's called the One Small Step to Protect Human Heritage in Space Act.
Actually, a good name for it.
Yeah, it is. That's right. Well, you can see where it comes from, can't you? Because that one small step is still there. Neil Armstrong's boot prints are still on the moon. They'll probably be there for 1 billion years or so until things just start sliding around due to solar radiation and things of that sort. But it's basically the intention is exactly that, to protect the American and, of course, other landing sites on the moon, because there are not just American sites, there are Russian, Chinese sites as well. So it's the first time that a law such as this has been enacted by any nation, and it seeks to sort of be a parallel to things like the World Heritage Convention, which lists historic sites Machu Picchu, for example, one of the most fabulous places I've ever been to, a site of kind of beyond value in a sense, because it is just it speaks of a time in human history when the Incas were building this extraordinary city in the clouds. So it's the commentary I've read about this law has been welcomed by a space lawyer. I think it's really one of the other things that's nice about it is that the Act has gone to into legislation in an environment that is very politically divided. And one of the comments made by a commentator I've read is that it shows that space and our attempts to preserve things in space is a non-partisan venture, and perhaps even to some extent a unifying venture, which is very nice.
Well, we could use some unification at the moment with everything that's been going down lately.
We certainly could. That's right. So yeah, maybe space is the way. It's one way to heal some of the rifts. It's I think a great step forward. I think you and I might have talked a few years ago about a push to try and get some of the lunar landing sites recognised as national parks by the American National Parks and Wildlife Service, or whatever their equivalent is in the United States. But that foundered because a national park's got to have a fence around it. and it's a bit hard, It just basically didn't qualify. So,
that's funny.
That didn't go any further.
You'd think it might be easy to change the law that the fence wouldn't be required for an off-planet site.
Well, yes, but then you suddenly, you're back in the depths of murky legislation,
bureaucracy
things of that sort. Bureaucracy, yeah.
Yeah.
Anyway, it is a very nice story, and I welcome it. I think it's a great idea.
Yeah, and it's not just the Apollo 11 landing site. I'm looking at the list of potential sites of that they want to protect on the moon. And it goes up to as recently as the 1st of December last year with the Chang'e 5 landing.
Chang'e 5, that's right. Yeah.
So, and they're all significant achievements in science, because
very much so.
We take it with a grain of salt these days that launching things into space to do whatever mission on whatever body of Earth or ground beyond Earth it is, whether it's Mars or Venus or the Moon or Pluto or whatever. Not that we landed there, but it stands to reason that these are incredibly high-tech achievements, very, very difficult to achieve. You can't just say, I'm going to send a falafel to the moon. Well, actually, you probably could, but what I'm witnessing now is that these events have inspired the people of today to start doing extraordinary things. And there was a story the other day about somebody in the UK, I think, who launched, he's got a takeaway food shop, and he's launched one of his products into space. Now, it landed in France, by the way, but okay, it was a publicity stunt, but he did it.
Yeah.
He actually achieved a suborbital launch of whatever. I can't remember what it was, but it was some kind of food. And lots of people are starting to do things like this now. So it sort of sets a new agenda for the future of space and science. I think it's fabulous. And so protecting these important sites, I think, it's a great idea. Fabulous idea.
It kind of has, what you've just said, though, has echoes of protecting our night skies as well, which, of course, is one of the issues that faces the satellite constellation lobby. For example, SpaceX and OneWeb is another company that's going to launch mega constellations of satellites. Then you're faced with another question. How do we preserve our heritage of a pristine night sky, which is one we've got to face? So, but my view is that there's a balance between these things. It's we must be able to find a way that satisfies both the requirements, the technological requirements for perhaps bringing internet on a global scale, and set that against the requirement to keep our night skies as unpolluted as possible. And actually, I have to say, SpaceX is working on that with their visor satellites to keep the light coming back to the ground.
And of course, there is also the potential to protect future landing sites in other parts of the galaxy, such as the site where the first woman will step on.
That's right. That'll be important.
That which I think they've got planned for 2024.
Yep.
At this stage. So that would be something very worthwhile protecting. Does it cover things beyond the moon? Do we know? Are they sites on Mars?
Look, I think my understanding of the spirit of the legislation is that, yes, it is not just about the moon. I might have misread that, but that was my understanding, that covers other worlds as well.
Yeah, well, there'd be quite a few on Mars. Viking would be probably one of the significant ones, but not just that. And I mean, you'd even have to probably take into account some of the not so successful missions, some of the landers that just failed to wake up, or some of those unfortunate crashes that all help us to learn from our mistakes to achieve success.
Beagle 2, for example. Beagle 2, the one that
Beagle
didn't open its solar panels. Yeah.
Yeah, which was lost for years, but somebody found it. We did a segment on that not so long ago. There are all sorts of amazing missions that would qualify. And, the time may come when we're occupying the moon. Who knows how many people might be living there at some time in the future. They'd be able to go out and look at these like you go to a museum. And I think it'd be exciting.
Yeah.
I reckon. Yes. Anyway, it's a great law, and it's one that is probably, I wouldn't say overdue, but definitely good timing to introduce it. So some of these amazing sites from some of the great space journeys in history are now going to be protected for years and years to come. You are watching and listening to the Space Nuts podcast with Andrew Dunkley and Fred Watson.
A lifetime of hard work, children laughing in the kitchen, family photos on a restaurant wall, a legacy that lives on. It all comes from the power of a conversation, like the one Tommy Hall had with First Horizon Bank about taking over his father's Charleston-based restaurant business. Now the table is set for a whole new generation. First Horizon Bank. Let's find a way. Go to firsthorizon.com/Tommy. First Horizon Bank, member FDIC.
3, 2, 1.
Space Nuts.
Thanks for listening to the Space Nuts podcast. This is episode 236. And we only started yesterday. It's amazing how fast time flies. Now, I want to say thanks to our social media followers, because without you, we wouldn't have a social media presence. And our Space Nuts Facebook page is proving to be continually popular. We've got just so many people following us there, and lots of material gets posted there. And I'm just scrolling through it now and looking at some of the stuff that's popping up. It's terrific, and lots of views and lots of comments. It's a site that gets a lot of engagement. We're also on Twitter. We're also on Pinterest. We're also on Instagram. And of course, the ever popular Space Nuts podcast group, people still joining that in droves. And that's a place where you can join other Space Nuts listeners and chat to each other and post pictures you might have taken. Now, Fred, remember not so long ago we were talking about when they publish scientific or astronomical papers and they put the authors at the bottom, and there's usually 1 million people that have contributed. Well, Bobby Jim Scott has posted a picture on the Space Nuts podcast group page. Hey, Fred, you mentioned being on papers with lots of authors. Have a go at this one. This is the comparative host coronavirus protein interaction networks reveal pan-virus disease mechanisms, and the list of authors. Actually, I've got a camera so I can show those that are watching. There's the list of authors.
Yeah, that's very similar to some of the physics papers that we see. Yeah.
But see, that's the sort of thing people are doing on the podcast group with each other, and it's it's a lot of fun, and being like-minded, you can all talk to each other, and sometimes people post questions, and everyone has a crack at answering them. It's a really good page if you want to join it, the Space Nuts Podcast group. Okay, let's carry on. And our next topic, Fred, is to do with gravitational waves. Now, we've talked about them several times recently, now that we're starting to detect more and more of them and learn how to detect them. And I guess that's what this story is about, detecting gravitational waves using an observatory the size of a galaxy. Now, I'm guessing that nobody's actually built one like that, not even the white mice, but we are taking advantage of natural opportunities, I imagine.
You've got it in one, Andrew. That's absolutely right. What really interests me about this is the different flavors that gravitational waves come in. And it's all about frequencies. The frequencies of gravitational waves that we've detected with detectors like LIGO in the United States, Virgo in Italy, and I think there are others operational now. They're actually in the audio frequency range. They're things that you amplify them, plug them into a loudspeaker, and you could hear them. And I think many of us have heard the chirp sound whoop, as it goes when you've got two black holes merging or two neutron stars merging. It's because the frequency increases very rapidly with speed, with time as they come together. However, so the gravitational wave detectors that have been built so far are sensitive to this frequency range, but the frequency of gravitational waves is a very big thing, and I read about it quite some time ago now. I can't remember. It might have been when I was writing Exploding Stars and Invisible Planets. I was reading about the different frequencies of gravitational waves that you can get. And some of the most interesting ones are really low frequency gravitational waves. So rather than being, 500 hertz, where 1 hertz is 1 cycle per second, which will be an audio wave, 440 hertz is A, if my musical skills haven't deserted me altogether. 440 hertz, very much in the audio range. But there are things you can learn from much, much, much lower frequencies. And there is a project which has been going for more than 13 years, and I wasn't aware of it. It's American and Canadian astrophysicists. They have something called the North American Nanohertz Observatory for Gravitational Waves, which abbreviates to NanoGrav. North American Nanohertz Observatory. So what's a nanohertz? Well, it is a billionth of a hertz. It's something that has a frequency of 1 billionth of a cycle per second. And I did a very quick calculation yesterday that told me that to get the full cycle at that frequency, you have to wait 31 years. That's a billion seconds. So you can see they're not wiggling around in the audio frequency range. They change the gravitational intensity changes, glacially slowly. But the reason why this is of interest is that there is a theory that suggests that there should be, and I'm quoting here from the phys.org article, which I think has actually come from the University of Colorado at Boulder. I think it's their press release. But they say rather beautifully that there is something called the gravitational wave background. That is what scientists call the steady flux of gravitational radiation that, according to theory, washes over the Earth on a constant basis. I like that idea. But it's washing, the waves that are washing over the Earth have the effective wavelength, it takes them 31 years to get one wavelength going past. And so that's the issue. But, ridiculous as it sounds, there are ways to try and detect that. And what they involve is looking at the timing of pulsars. So this is why this is spread all over the galaxy, because these scientists have used pulsars which are distributed through the galaxy. I can't remember how many of them there are at the moment. I think they're trying to increase their numbers. I should say, by the way, this is one of the stories that's come up. January is always big for stories coming out of the United States because it's the time when the American Astronomical Society has its meetings, and at the moment the 237th meeting is going on, so they've been going for a while. Anyway, what are pulsars? Pulsars are neutron stars, highly condensed remnants of giant stars that have actually gone supernova, and the neutron star is what's left, but they're beaming out electromagnetic radiation from their magnetic poles, and they're rotating very quickly. In fact, the millisecond pulsars rotate 1,000 times a second, which is phenomenal for something that's 10 kilometers in diameter, going around at that speed, with all these intense magnetic fields which are beaming out the radiation that we see as these pulses. Now, the thing about pulsars is that their radiation is extremely regular. So forget about atomic clocks. A pulsar is more regular than an atomic clock is. So that the bursts of radiation each time it rotates. And that is what gives you the scope for trying to detect gravitational waves by these objects. Because if you can see the regularity of these pulses changing in a, what you might call a predictable way, and changing out of phase by these pulsars that are spread over vast tracts of the galaxy, then you've got a chance of detecting these nanohertz gravitational waves. It's a I think a remarkable piece of astrophysics, that even the thinking behind this that's going to let you do it is quite phenomenal.
Yeah, I think they're talking about 45 pulsars, I believe.
Thank you. Yeah. I missed that. But that's, they're spread around the galaxy. Those 45 pulsars are actually giving you, basically a three-dimensional fix in terms of how you can register these gravitational waves going through. The technology behind it is something that I haven't really looked into, and it's quite difficult, I think. But I think it's a great idea. I'd love to follow up a bit more on that, and I might have a look at their paper when the dust settles a bit.
Would it be, by way of my brain turning it into a rudimentary explanation, the same kind of approach as putting an atomic clock on the ground and one in a plane, and then looking at the difference when you put them back together? Is that what they're doing here with pulsars? Yeah,
that's pretty well put it in a nutshell, Andrew. A very nice analogy, because the well done, because it is all about. In that sense, you're looking for gravitational time dilation as the gravitational wave goes through. I was very interested, once again, going back to the reading that I was doing when I was writing about these things in Exploding Stars. There will be gravitational waves that will come from the Big Bang itself, but they, I think, have a wavelength that's even longer than the ones we're talking about, where you're talking about not 31 years for the whole wave to go past, but 1 billion years for the whole wave to go past. So how do you detect that? Well, we don't have mechanisms at the moment.
Yeah, but maybe one day.
Maybe one day, yeah.
It makes you wonder what else is bouncing around out there that we don't know about or haven't been able to detect as yet. I mean, we're reaching a point where we're starting to discover things we didn't even contemplate 20, 30, 50 years ago. Yeah. And that makes you wonder what we might find in 50 or 100 years' time that we can't even think about now. I mean, that's the nature of it, isn't it? We just keep finding all these unusual things and trying to figure them out, like dark energy.
Yeah, exactly. Dark energy was exactly what I was going to mention. That's, one of the theories for what dark energy might be is something called quintessence, which is a fifth fundamental force. And there's hints that there might be something like that around, but at the moment nobody really believes it. But you never know. In 20 years on Space Nuts, when we're in our wheelchairs, we might be talking about quintessence.
Yes, but the beauty of it is the technology exists for us to continue to do Space Nuts from wheelchairs.
Yes,
so
that's right.
that would be fine.
Might not be very riveting.
It'll be a lot slower.
How's your back doing, Andrew? How's your back keeping?
Well, I've got enough metal in it to start my own fusion generator.
Good.
Thank you very much.
Right.
Oh dear, enough of this frivolity. You're listening to Space Nuts, Andrew Dunkley and Professor Fred Watson.
Experiences are what people love the most about travel. Viator is a website and app where you can book travel experiences like hiking Mount Kilimanjaro in Tanzania or enjoying the views while cruising on a catamaran in the Caribbean. They offer everything from simple tours to extreme adventures. With over 300,000 bookable experiences in 190 countries, there's something for everyone. Plus, Viator's travel experiences have millions of real traveler reviews, so you have the information you need to book the best activities for your trip. When you book a travel experience with Viator, there's always flexibility and support with free cancellation, payment options, and 24/7 service. Download the Viator app now and use code Viator10. That's Viator 10 for 10% off your first booking in the app. One app, over 300,000 travel experiences you'll remember. Do more with Viator.
Space Nuts.
Welcome back, and thank you for joining us on the Space Nuts podcast. I'm Andrew Dunkley, and he's Fred Watson. If you want to be a supporter of the Space Nuts podcast, and we're talking about, money, there's a way of doing that via our website, spacenutspodcast.com. One of our plans, I've been talking about this with our producer, Hugh, one of our plans is to ultimately make Space Nuts commercial free for everybody, and we want to do that by way of patrons. And of course, we've got several patrons right now who support us voluntarily, and it will always be voluntary. But if you would like to join their ranks and get a bit of extra special treatment, like the commercial free edition, you get it earlier than everybody else, and you get bonus material. You can do that on our website, spacenutspodcast.com. Up in the top right-hand corner, there's the Support Space Nuts button. Once you press that, you've got options to become a patron through Patreon, Supercast, or just make a donation via PayPal. It's totally up to you. And like I say, every week it's not mandatory, but we want to try and get ourselves to about 1,000 patrons, which would enable us to basically shed the commercial side of the venture, which is the goal of us. So have a think about it, and if it's something that you would like to do, and it's not going to be an overly expensive prospect, it's really up to you. We'd be greatly honoured and very appreciative of your generosity. If it's not for you, it's not for you. So that's something to think about. So spacenutspodcast.com, and then click on the Support Space Nuts button in the top right-hand corner. Now, we've got some questions to deal with, Fred, and our first one is coming today from Houston, Texas, and it's from Jonah.
Hi, Fred. Hi, Dave. This is Jonah from Houston. I have a question about one of the more popular topics on the show, black holes, specifically about Hawking radiation. Now, I've heard Hawking radiation explained as being a phenomenon due to the existence of virtual particles and their behavior. Now, I've looked up lots of YouTube videos and lots of articles to try to understand virtual particles, but I cannot wrap my head around it. Can you possibly shed some light on this? All right, thanks, guys. Love the show.
Thank you, Jonah. The answer is no.
The answer is not far from no, actually.
Yeah, look, we've sort of talked about Hawking radiation before. I'm not sure we've really done a lot on virtual particles, but that's probably because it's one of those realms of astronomy and space science that is still very much shrouded in theory, I would imagine.
It is. It's really interesting stuff, Andrew. And thank you very much, Jonah, for sort of probing this a bit, because we do tend to talk about these things quite glibly. And just for background, for anybody who's not up to speed on this, Hawking radiation is thought to be the result of the popping into existence of particle pairs in space, one of which gets trapped on one side of the event horizon, the other which gets trapped on the other side and is released effectively as a real particle, a radiation, whereas the other one sinks down into the centre of the black hole very quickly, probably. So yes, we, as I said, we bandy the term around, virtual particles, without really giving that much thought to what it means. And in some ways, that is kind of what physicists do as well. And so what I've done is I've gone to the Wikipedia page, which is actually very detailed about virtual particles, and just try to unpick some of the ideas that are in there, which I hope might shed a bit of virtual light on the situation. There's a definition which is complete gobbledygook. In physics, a virtual particle is a transient, that means temporary, quantum fluctuation, that means it's something on very small scales, that exhibits some of the characteristics of an ordinary particle while having its existence limited by the uncertainty principle. Now, that goes straight to quantum physics. The uncertainty principle says that you can know the momentum of an object or its position, but not both to the same level of accuracy. This is in the quantum world. And it's been well established. That's something we know. You discover the details of its position, and you don't know its momentum to the same level of precision, and the other way around. So that's the formal definition, but it really doesn't help very much. So skipping down the Wikipedia entry, I like this because this sheds a bit more light on it. The term is somewhat loose and vaguely defined in that it refers to the view that the world is made up of real particles. It is not. Real particles are better understood to be excitations of the underlying quantum fields. Virtual particles are also excitations of the underlying fields, but are temporary in the sense that they appear in calculations of interactions. I won't go on because it gets back to gobbledygook. It talks about asymptotic states and indices to the scattering matrix, so we don't need to go there. But the key thing is, and I think this is, really the bit that makes it interesting. Actually, let's just read this bit too. Virtual particles do not necessarily carry the same mass, as the corresponding real particle, although they always conserve energy and momentum. That's sort of a bit related to the uncertainty principle. The longer the virtual particle exists, the closer its characteristics come to those of ordinary particles. And this is where the crucial bit is, I think. They are important in the physics of many processes, including particle scattering and Casimir forces. Casimir forces are forces that exist in a vacuum for no apparent reason. So virtual particles do that. Oh. But the key sentence, I think, is this one. In quantum field theory, forces such as electromagnetic repulsion or attraction between two charges can be thought of as due to the exchange of virtual photons between the charges. So virtual photons are the exchange particles for the electromagnetic interaction. So what this is saying is that in order to understand some of the well-established and well-known physical processes, but to understand them at the quantum level, you actually need virtual particles. So they must exist. And the final sentence of the Wikipedia introduction puts that in a nutshell. It says, the accuracy and use of virtual particles in calculations is firmly established, but as they cannot be detected in experiments, deciding how to precisely describe them is a topic of debate. So that's really what it is. So the answer is nobody can really put their finger on, what virtual particles are all about. But we know they exist, and so Jonah's question is right on the money. It's something that, it doesn't matter how many YouTube videos you watch, since the physicists don't understand it, the YouTube video makers aren't going to understand it either. It's a really interesting field, but a great question, and good to be pushed into thinking a little bit about this a bit more. I'd recommend the Wikipedia page on virtual particle, but I would warn you that it does get really very technical. But I think there are parts of it you can kind of, just skip through it, and you will find parts, sentences like some of the ones I've read out, that really illuminate what the problem is and, what it is we're really talking about.
And Jonah shouldn't feel bad that he can't get his head around it, because nobody can. And therein lies the problem. But for the second time in this podcast, I'm going to try and bring it down to my level and say virtual particles sound to me like a temporary file on a Windows.
One that pops into existence and then pops out again. Yeah. Well, you should get a Mac.
Exactly.
Oh, you have got a Mac.
I have got. Yeah, I have. I've got one.
No, that's right. See? That's a good analogy too.
Not doing much at the moment, I'm afraid. But yeah, Jonah, thank you so much. That was a great question, and one that is probably, it's fair to say, in the very, very, very early stages of investigation, and who knows how and when we'll ever figure it out, if we ever do. Okay, let's move on to our next question. It's from Jacob in Phoenix, who says, "Hey, Andrew and Fred, I hope you're both doing well." I'm doing well. Are you doing well, Fred? Yeah, we're doing well, Jacob. I have two questions, if I may. One, I always see movies that have to do with space, and I never really see stars below a spacecraft or camera view. Are there stars below you if you're, let's say, floating out in space, or is there only stars behind or in front of you based on the way the universe expands? If there are stars and galaxies below your feet, could you ever travel to them? Second, are we close to any black holes closer than the one that is 1,000 light years away? Are black holes able to change direction to where we may be a victim of their power later down the road? Thank you both for your work and consideration in regard to answering my questions. Best, Jacob. Jacob, wonderful questions. I because I love science fiction, I do recognise what he's talking about when it comes to some of the scenes in space travel. Well, we've got to remember they didn't really go up there and film, so we have to take the word of astronauts and observation platforms in space that portray these things in reality. But yes, I would imagine, given the shape of the universe and the expansion of the universe, even though it's technically a disk, the universe itself, we've determined in past episodes, it's spherical. There would have to be stars below us. Maybe not as many as there are behind, in front, and beside us, but there would have to be, wouldn't there?
Yes. So what you were talking about with the disk there is our galaxy, and we see that as the Milky Way. But the bottom line is, you've only to think about the Earth's position in space. From all points on the Earth, you can see stars, and that's telling you that formally there's no definition of up or down in space. We just actually have this definition of north and south in space, but it's completely arbitrary. The stars are there, and it's not really. I take Jacob's point about, does the expansion of the universe change things? And the answer is that the expansion of the universe is something that you simply don't see until you really start looking very deeply into space with big telescopes, and you can detect it. But in terms of our existence, the the stars are static. They're all over the sky. So if you're floating in space with no planets near you or nothing to block your view, you'll be able to see stars all the way around. Which is, it's kind of what you might expect. The second question about the black hole, I'm not sure of an era one. 1,000 light years rings a bell. I think we've talked about this one before as being one of the nearest ones. Are they able to change direction? Well, they're bound by the same rules that that govern everything else, the movement of everything else in the universe, and that's gravitation. A small black hole, the result of perhaps an exploding supernova, will move along with the other objects in its locality as it goes around the galactic centre. Of course, the galactic centre black hole stays put because it's right at the middle. But yes, they simply orbit. So unless they interacted, if two black holes kind of had a close encounter but didn't merge, then you might get one of them being shot out in a different direction. And for us to be exactly in the line of sight of one of those accidents would be very unexpected. It would be a rarity, but I guess it's not impossible is the bottom line. But they don't just, the main thing about black holes is they don't just say, oh, I think I'll go this way now. They are bound by the rules, just like everything else in the universe.
Yeah. There you go. But we'd have to be super duper unlucky to have something like that happen. Oh my word! I can't imagine what the effect would be, but it would probably take a very long time for one to reach us. Like we were talking last week about how long it would take for an influence on the Oort cloud to send comets our way, 50 to 100,000 years. I suppose it would be similar with a black hole.
Yeah, that's right. It would, and there's nothing coming our way at the moment, and time is on our side.
Well, I suppose if it did happen, if a black hole did somehow get bumped into a collision course with Earth, we'd know about it long before it destroyed us. I imagine we'd start to feel some weird.
Well, just by the way you detect the presence of a black hole is by its influence on its surroundings, and you'd know just by normal astronomical observations that there is something on the horizon. I mean, we know that already. The black hole at the centre of the Andromeda galaxy will come very close to the black hole in the centre of our galaxy in about 3.5 billion years. So you get enough warning. That's the bottom line. We know about these things.
Yeah. And hopefully we'll be able to escape its clutches or be long gone before that even becomes a problem. Yeah. Indeed. Thank you, Jacob. Great questions and really appreciate it. And of course, if you have questions for us, please send them in because we are a bit light on. I mean, we could obviously do an episode without questions, but we like to do the questions. We love to hear your voices. We love to hear from you. We love to hear what you're thinking about, what you're wondering about, and we do love to try and tackle some of these questions. And as I mentioned last week, I love those what-if questions. What if another planet turned up in our solar system and bumped Pluto onto a collision course with Earth? What would happen? Things like that.
Well, you've come to the right place, Andrew.
Yeah. Yes, indeed. So you go to our website, spacenutspodcast.com. You can send us the question via our email interface. It's pretty easy. Just fill in the blanks, or you can click on the AMA tab and record using your voice or someone else's if you want to hire a professional. That's totally up to you. But if you've got a device with a microphone in it, it's really as simple as pressing the button and going, "Hi, I'm Fred from Sydney, and I have a question about Maseratis."
That's funny you should say.
When can I have one? But yeah, it's as simple as that. So we'd love to hear from you, and we'd certainly like to gear up with a few more questions. And it's like disturbing the Oort cloud. When I ask for more questions, there's not an immediate response, but we eventually get bombarded. So that's how it always works. So looking forward to hearing from you, especially if you've thought about it and never done it before. Bite the bullet. Yep. We want to hear from you, please. Okay, that wraps us up for another week. Fred, thank you so much. Great to see you. Great to hear you. Great to talk to you. Great shirt, great everything.
Oh, thanks. Glad you like the shirt. Thanks, Andrew. And we'll speak next time.
We will indeed. Professor Fred Watson, astronomer at large, part of the team here on the Space Nuts podcast. And thank you for watching. Thank you for listening. Whatever platform you follow us on, we appreciate it. We'll catch you next time on another edition of the Space Nuts podcast. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.
Hello, Saver. Whether you're saving for that trip to the tropics or saving for an emergency, now is the time to take advantage of Wells Fargo's savings options. Wells Fargo offers savings accounts that can help you save towards your goals. So, what are you saving for? Visit a Wells Fargo branch or wellsfargo.com/save to open a savings account today.
Wells Fargo Bank, N.A., member FDIC.